Hello everyone, this is Miss Lindsay. Today we're going to talk about inverse trig functions. If you recall from earlier in the year, we found a test for functions to determine if it has an inverse. And we also discovered why does it work. Well, the test is the horizontal line test, and it works because it shows if a function is one-to-one. If the function is one-to-one, then it has an inverse. So let's think about how this relates to one of our trig functions, and specifically sine. If we graph one single period of sine, just a sketch of it, would this pass the horizontal line test? And hopefully you see if we draw one horizontal line on there, it would hit more than one point. Therefore, it is not one-to-one, so it does not pass this test. So we will actually come up with some restrictions on the sine function in order for it to actually have an inverse function. Before we do that, let's talk about how we do this algebraically. If you recall again from previous units, we switch x and y, and then we solve for y. So in our function here, cosine x equals y, if we switch x and y, and to solve for y, we need to take the inverse cosine of both sides, which we have done in the past, and that would be our inverse cosine function. Let's talk a little bit here about some notation. So remember, when you have cosine theta equals a value, theta is the angle, and it can be in degrees, but we typically work in radians. And then the value is the ratio of the sides of a triangle. Okay, it is not an angle, it is a ratio. So again, in our cosine function, we take cosine of the angle, and that equals a value. However, in the inverse cosine, we would take that of the value, and our result would be an angle. So in other words, I would like to typically say, when we take the cosine of what value, we'll get that value. That is what this actually is asking. Okay, so really important to understand that we are now switching the places of x and y, so we're actually getting the angle value out when we're taking the inverse. Again, some notation here. Okay, so again, we've seen this on the left before when we've been working with our trig functions. On the right, this is a little bit different. You'll see that we have arc cosine, arc sine, arc tangent. That is exactly the same thing as taking the inverse of tangent, or the inverse of sine. So this is interchangeable notation. So inverse of sine and arc sine are the exact same thing. So now let's go back to our original question here. This did not pass, sine of x did not pass the horizontal line test. So we do have the typical domain of the sine function is all real numbers, and the range is -1 to 1. We are going to restrict this domain, however, to be from -pi/2 to pi/2. And again, we're restricting it so that, again, every function value is included, and now our domain is going to go from -pi/2 to pi/2. And our range will remain the same from -1 to 1. Let's do this exact same thing for cosine. How again can we restrict this domain so every value is included? Here we're going to cut it off at 0 and go to pi. So again, our domain goes from all real numbers now to from 0 to pi, and our range remains unaffected from -1 to 1. Tangent, again, if we restrict this, here we're going to restrict it from our first asymptote of -pi/2 to pi/2. And so again, our domain now goes from -pi/2 to pi/2. However, the endpoints are not included because these are asymptotes, and the range will remain the same as the original function, all real numbers. So how does this have an effect on our inverse functions, or in other words, our arcsine, arccosine, arctangent? Well, if we remember, if we do the inverse of tangent, right, we switch x and y. Therefore, the inverse of tangent, we would switch our range and our domain. So our domain of our original function tangent will now become the range. The range of the original function tan of x now becomes the domain of the inverse. So here is a chart that you need to know for our inverse function. So as you can see here with arcsine, the domain and the range would flip from the sine function. So now our domain becomes -1 to 1, and the range goes from -pi/2 to pi/2. Same thing with arccosine. The domain -1 to 1, and now the range is 0 to pi. Arctangent, domain is all real numbers, and the range is -pi/2 to pi/2. So let's try some examples. Over here on the left, we want to solve between 0 and 2 pi. The tan of theta equals 1. So in other words, what angle, when we take tangent of it, gives us a value of 1. So if we look at our unit circle here, we're going to see that we have, our first value of pi/4, and then also 5 pi/4. Well, how does it differ from arctan of 1 over on the right? Well, because this original function has arctan in it, we have to think about our restrictions. Our restrictions on our range now go from -pi/2 to pi/2. So now we are only looking from pi/2 to -pi/2, so we're looking at the first and fourth quadrant. So you can see that now 5 pi/4 is not in those quadrants, so our only answer would simply be pi/4, because that is the value that fits in the range of arctan. So if your original problem has arctan or the inverse of tan, you must think about the restrictions. However, in a problem on the left, it does not have inverse of tan or arctan, therefore we do not necessarily we do not look at the restrictions. So let's take a look at another problem. So here we have cosine of theta equals -1/2. So again, where is our y value? Where it equals -1/2. So we get that to be 2 pi over 3, and then we also get that to be 4 pi over 3. Now we have the inverse, so we're thinking again about the range, the restrictions here, and that goes from 0 to pi. So we're now looking at the first and second quadrants. So again, that rules out 4 pi over 3, and we simply would just have 2 pi over 3. Okay. Take a look at our next example. This one is sine of theta equals -√3 over 2. So again, now we're looking for our y value, and in this case we have that to be 4 pi over 3 and 5 pi over 3. Now we have our restrictions to think about, again, which go from -pi/2 to pi/2 for arc sine. So we're looking at our first and fourth quadrant. And the most logical answer would be say, well, it's 5 pi over 3. However, 5 pi over 3 does not fit in our range. It needs to be the negative angle in the fourth quadrant. So there's a couple different ways to think about it. You can think about it in terms of doing the coterminal angle, where you take 5 pi over 3 and subtract 2 pi. Or you can simply count in the negative direction like we've done before. So it would be -pi over 6, -pi over 4, -pi over 3. Therefore, our answer here would then be -pi over 3, because that's in the fourth quadrant and it fits in within our restrictions. Let's take this one step further and think about the composition of functions. If you recall from composition of functions, if f and g are inverses of each other, f of g of x equals x, excuse me, and g of f of x equals x. Well, this rule applies occasionally or sometimes in the composition of our trig functions here, but again we have to think about some of our restrictions. So in this first one we have arctan is in the inside, so we have to evaluate this one first. So we have to think about whether or not 36 is in the domain of arctan. And the domain of arctan is all real numbers, therefore the answer to this is yes. So when we take tan of the arctan of 36, it would simply be 36. However, on our next problem, now the inverse is on the outside. So we must look at 5 pi over 4 and ask ourselves, is this in the range of the inverse of sine? So the range goes from negative pi over 2, so the answer to pi over 2, so the answer to this question is no. Therefore, we actually need to calculate this out by hand. So we'll look on our unit circle, 5 pi over 4. When we take sine of 5 pi over 4, we will get that to be negative root 2 over 2. Now when we take the inverse sine of negative root 2 over 2, we have our restrictions that are between pi over 2 and negative pi over 2. So we take a look, and that would be 7 pi over 4. However, we need to think about the negative angle. Therefore, that would be negative pi over 4. And you can actually verify specifically this first one in a calculator. I would like you to try to do these without a calculator and think about the restrictions and checking the restrictions. However, okay. I would like you to go ahead and pause at this point in time. Try these two examples, push play when you're ready to check your answers. Okay, so again, checking your restrictions here, because our the inverse sine is inside, we have to check to see if negative 0.3 is in the domain of the inverse of sine. It is, because it goes from negative 1 to 1, therefore it's simply just negative 0.3. Then when it goes, the inverse of tangent goes to the outside, we now check to see if this pi over 3 is in the range of the inverse of tan, and again it is, because that goes from negative pi over 2 to pi over 2, therefore is simply pi over 3. And let's finish up with these last two examples here. Again, since arc cosine is in the inside, we check to see if 36 is in the domain of arc cosine. And again, arc, I misspelled that. Okay, it is not, because that goes from negative 1 to 1. Therefore, this does not exist. And moving on over here to our last example, because arc, cosine, and tangent are not actually inverses of each other, we need to take a look and actually calculate these. So I will figure out that we have tan of 7 pi over 4. If you take a look here at 7 pi over 4, we get that to be a value of negative 1. Now we take a look at arc cosine of negative 1. What angle gives us that? And that goes between 0 and pi. So we're taking a look here and seeing that pi would give us, if we took cosine of pi, that gives us negative 1. So again, checking to see the restrictions on all of these functions, especially when you're doing the compositions, is a time saver. And again, you do need to know the domain and range of the inverse functions. Okay, and here is your homework for this evening.